Hello and welcome to my presentation on Boomwhackers and the speed of sound in air. I'm Bernard Taylor and this is Fez Physics, so let's get moving. What are Boomwhackers? Boomwhackers are these plastic tubes, nice different colours, open at both ends, which you may be familiar with from primary schools. You hit them against your palm of your hand and you get a characteristic frequency for different lengths of tube. You can buy them easily from Amazon, sadly not one of my sponsors, and there are groups like Thud from Harvard who do some amazing performances with Boomwhackers. So let's see how we would use Boomwhackers as the basis of a possible core practical. I've got my computer microphone here and my computer running Audacity. It's free software, very useful. And I've got three different lengths of Boomwhacker here. Let me take the longest length Boomwhacker and I'm going to hit it against my hand. We could record this, but we're not going to at the moment. And we hear a characteristic frequency of sound. Let me take the shortest length Boomwhacker and do the same thing. And we get a different frequency, a noticeably different frequency. Let me take the intermediate length Boomwhacker, and again a different frequency yet again. Now, we need to get to grips with some theory before we go much further. So, in the top diagram on the left-hand side, I've got a tube which is closed at one end. And if I follow my standing wave pattern from here to the open end, that will be a quarter of a wavelength. If I went further, maybe to here, that would have been half a wavelength. So, lambda over 4, quarter of a wavelength, is equivalent to the length of the tube. Now, let's look at the right-hand side. Let's suppose that tube is 0.4 meters long. Let's suppose that the speed of sound in air is 340 meters per second. Now, for A, L equals lambda over 4. So lambda is 4 times L. So lambda is 4 times 0.4, which is 1.6 meters. And of course, this is for the fundamental frequency, the fundamental wavelength. Following on, using the wave equation and rearranging it, F equals V over lambda. So the frequency in this case will be 340 divided by 1.6, which is about 213 hertz. In the same way, for the tube at the bottom, tube B, if we go from the left-hand end to the middle, that will be lambda over 4, another lambda over 4 to the other end like that, and so that's lambda over 2. So L equals lambda over 2. So again, lambda equals 2 times L, which is 2 times 0.4, so lambda in this case is 0.8 meters. Again, a similar analysis leads us to F, the frequency of the fundamental, equals 340 over 0.8, which is 425 hertz. And you'll have noticed, of course, that that is double the frequency for tube A. But we're going to be working with Boomwhackers, tubes that are open at both ends. Let's get moving. If we take the wave equation, V equals F times lambda, and rearrange it to make F the subject of the equation, then we can see that if we're plotting a graph of F against 1 over lambda, then the gradient of that graph is the speed of sound in air. And essentially that's the journey that we're going to be on for the course of this presentation. When we're using Audacity to work out the fundamental frequency, we have our computer microphone, of course, but we would highlight a number of hits of the tube against our hand, and then we would go to the analyze function and get the spectrum analyzer, and that would give us this kind of plot, and this first lowest frequency peak would be our fundamental, and Audacity gives us that peak value quite nicely over here. Now let's remember that because we're using a tube that's open at both ends, we're using a Boomwhacker, then lambda equals 2 times L. So Audacity gives us the fundamental frequency, measuring the length gives us the wavelength. Okay, let's move on. Here's a table of results, and we've got different frequencies, we've got the lengths, we've got lambda, and we've got 1 over lambda. But is there anything missing here? You know, we're dealing with A-level physics or IB physics, and surely we should be taking into account uncertainties. And here I've tried to put in an estimate for the uncertainty in the frequency, an estimate for the uncertainty in the length, and for lambda, and indeed for 1 over lambda. Now, sometimes this may be a little bit more of an art than a science. It's pretty much of an estimate as to what delta F is. But I notice when I try to plot a graph that the uncertainty bars are actually too small to plot. And you've got to say that. And I would always recommend that you do it directly underneath your table of results. So what do we do then? Well, first of all, if we plot a graph of frequency against 1 over lambda, then we can see quite nicely that we get a straight line, what looks like a straight line. And my analysis gives us that the gradient, 440 divided by 1.4, is 314.3. So I could conclude that the speed of sound in air is 314 meters per second. But I'm not happy with that. What we should be aiming for is a graph that's clearly has the axes clearly labeled, has a title on it, something similar to my graph here. But we should also be looking for 2 slightly worse fit lines. And this is where it becomes more of an art than a science. We don't want those 2 slightly worse fit lines to be too close together, and we don't want them to be too far apart. It depends what our points are. But of course, that's going to give us 2 gradients. In this case, I've called it M1 and M2. Now, in calculating the 2 gradients, I want to get an average value, which is going to be an average value for the speed of sound in air. And over here, this represents, it's a handy way of representing what I'm trying to do. I've got the lowest value, 244, the highest value, 322, and I get the average value, 1 plus the other divided by 2, 283 meters per second. Now, what is the uncertainty? Well, the uncertainty, delta V, would be the highest value minus the lowest value divided by 2, which is 39 meters per second. So I could say that the speed of sound in air is 283 plus or minus 39 meters per second. I'd actually be happier with 280 plus or minus 40 meters per second, but the speed of sound in air varies with atmospheric pressure and temperature. So we really should be thinking about recording the atmospheric temperature. Okay, but we're not quite finished yet. We should be indicating how our value for the speed of sound in air differs from the accepted value. And we might, or we should, towards the end of our presentation, the end of our practical, have some kind of statement like this. The accepted value for the speed of sound in air is 340 meters per second, which is given in college physics by Pelcom and Narka, 1998. Okay, and my value is 83% of the accepted value. Fine. But there's something else to consider. The values that we get are a little bit below the accepted value anyway. And this is because of something called the end correction. Now, if we look at the top here, my diagram of the standing wave pattern, the fundamental standing wave pattern, with a tube that's open at two ends, in actual fact, the antinode here and the antinode here extend a little bit beyond the end of the tube. And this difference is known as delta C, which is called the end correction. Now, we had assumed that the antinode was at the exact end of the Boomwhacker tube. And I would recommend that you should try and do a little bit of research on the end correction, but please bear in mind that knowing about the end correction and using the end correction is not part of the A-level syllabus. So for a particular frequency, lambda would be larger than we assumed. 1 over lambda then is going to be smaller than we assumed for our particular values of f. And this would then give us a steeper line, a slightly larger gradient, and a slightly larger value for the speed of sound in air, which is what we are looking for here. So if you are carrying out this as a core practical, then you should certainly mention the end correction. So, thank you very much. That's Fez Physics. Watch out for my next Fez Physics presentation, and thank you for watching.